continuing with our reading of Individuation in the light of notions of form and information. We're starting chapter 3 of part 1 on form and substance. So maybe just a warning about this chapter is that this is probably the most difficult chapter in terms of the sort of prerequisites for it. In the next couple of weeks, we're going to get to the part on quantum mechanics, which and one particular interpretation of quantum mechanics that is not the standard one as well. Be prepared for that. It might be a good idea to take a look at the Wikipedia page on quantum mechanics and try to get a little bit of a sense of what's going on before we get to that part of the reading. But for today, I think it should be a little bit easier or a little bit less scientifically intensive compared to what we're going to get to in a couple weeks. Okay, so I'll start reading and then we'll go around as usual. So chapter 3, form and substance, section 1, continuous and discontinuous, subsection 1, functional role of discontinuity. The Socratic injunction whereby reflexive thought was asked to return to heed the call of ethics instead of physics has not been accepted in all philosophical traditions. According to Plato's expression, the sons of the earth have remained stubborn in their search through the knowledge of physical nature to find the unique solid principles for individual ethics. Leucippus and Democritus had already shown the way. Epicurus establishes his moral doctrine on the basis of a physics, and this same approach can already be seen at work in Lucretius's magnificent didactic and epic poem. But it is worth noting that one of the primary characteristics in the relation between philosophy and physics for the ancients is that the ethical conclusion is already presupposed in the physical principle. Physics is already ethics. The atomists necessarily define their ethics within their physics when they turn the atom into a substantial and limited being that passes through different combinations without changing. The composite has a level of reality inferior to the simple, and this composite that man is will be wise if he knows and accepts his own temporal, spatial, and energetic limitation. It has been said that the atom is minted Eleatic being, and in fact, as Parmenides reveals in his poem, which is a narrative of its initiation into being, the rounded and coined spheros, happy in its circular plenitude, fragments ad infinitum into the atoms, but it is always immutable matter, whether one or multiple, that confines being. The relation between the atoms of being, made possible due to the introduction of the void, which is substituted for the negativity of Parmenidean becoming, has no veritable interiority. Lawlessly emerging from countless dice throws, relation conserves through its existence the essential precariousness of its constituted conditions. For the atomists, relation depends on being, and nothing substantially grounds it in being. Emerging from a clinamen without finality, relation remains pure accident, and only the infinite number of encounters in the infinity of elapsed time has been able to lead to many viable things. Consequently, there is no case in which the human composite can attain substantiality, but he can avoid relations which, due to their groundlessness, are necessarily destructive and snatch for him the little time he has to exist by bringing him to think on death, which has no substantial reality. The state of ataraxia is a state in which the human composite concentrates on himself as much as possible and leads him to the closest state of substantiality that he can possibly attain. The Templa Serena Philosophiae makes it possible to construct not a veritable individuality, but the state of the composite conceivably closest to the simple. So here we're starting is a sort of a new beginning of the problematic of individuality, because here he's pointing to the relationship between physics and ethics with respect to the individual. And he points to the atomistic school, and then he's going to discuss the Stoic school afterwards and show that they have roughly the same, even though they have opposite visions of physics, they end up having almost the same conception of ethics with respect to the individual. In ancient philosophy, the ethical priorities or the ethical principles governing the individual are sort of dominating over the physics of the individual. The ethics is of an individual as a sort of self-contained, self-orienting substance, and that same substantiality is applied in the physics as well. So in the case of the atomists, it's the atoms that have that are individuals in the proper sense. They're the simple entities that have individuality, and then it's only through the Kleinamen that we end up with composite individuals, which are only in a secondary sense individuals. And so the Kleinamen, for those who, I think we discussed this early on when we were reading the introduction, but for those who may have missed that, the Kleinamen is in atomic physics the notion that the atoms falling in the void have to have a swerve in their falling so that they can join each other and form individuals in the composite sense. So the atoms falling in the void are falling vertically, and then there's this swerve that brings them into contact with each other and brings about the formation of composite individuals. And that's the Kleinamen. So it's the Kleinamen is the principle that governs the formation of composite individuals. And then in the ethics, the behavior of the individual of a human being is supposed to be modeled on this substantiality, so that the individual human being should try to act as if they were a substance, an atom, something individuated as much as possible, even though as a composite, you can never be fully, you can never behave fully as an individuated being in that sense, because the composite is always only secondarily individuated.
I really like this section as a statement of kind of principles of what he's arguing against. And it just seems kind of like a restatement of some of the things you've been saying earlier in the setup to this section. But I really like, essentially this point that, if you don't take, as Simondon does, relation to have the status of being, then, everything is going to seem like an accident. And so there's that I really like that statement that physics isn't ethics, because it almost reminds me of a Bakhtin kind of thing. There's no non-oriented intervention in life. There's no non-oriented theory, that they're all making a kind of orientated and, by definition, moralistic claim, which even goes back to his discussion of the singularities and the clay and the mold example, that these examples in ancient philosophy aren't just abstract logical scenarios, but they kind of already contain within them, moralistic assumptions about how things should be carried out, and ignore, in the case of the clay, all the preparation and the half chains that go towards preparing these singularities and preparing the colloidal properties and all that stuff we read. But anyway, I like this. As Angus was saying, apparently he gets into the photons and the much more difficult stuff at this beginning part.
Yeah, the only sort of qualification I would make to that is that he does, in a little bit, he specifies that this relationship between physics and ethics that we find in ancient philosophy is partly a weakness of ancient philosophy. That later, when we have, he's going to attribute this to the Christian notion of the individual as sort of separating physics from ethics and making it possible to have a true physics of the individual. But we'll get to that in a little bit. But yeah, so this interrelation between physics and ethics is not necessarily something that he thinks is universal, because he thinks that we can have a physics of the individual which is not determined by an ethics in the way that the ancient physics was. So that's what he's going to work towards. But it's not to say that there aren't going to be ethical implications of that physics.
From what I know from the Combs book about Simondon's ethics, it seems like for him maybe it's the other way around. The ethics follows from the physics rather than the physics being determined by the ethics. I don't know if that's right, though.
Yeah, that seems like a good formulation. I think, yeah, we'll see a little bit further why he thinks that the Christian notion of the individual in ethics sort of frees physics from its subordination to ethics, and and that sort of makes room for physics to develop a notion of the individual, which is not derived from ethics. So that's sort of the movement of the historical progression of the notion of the individual for Simondon, and it's also something that one of the supplementary texts in the second volume of the translation on the history of the notion of the individual goes into this in more detail. The notion of the individual in the atomists and the Stoics, and how it changes over time. But I guess we'll eventually get to that, but it'll be months from now. But yeah, I think physics determining ethics is a better formulation than the ethics formulating determining the physics.
I just we don't have to answer this now, but maybe just something to keep in mind as we're piecing through this stuff is when we're saying this about ethics, I guess is Simondon talking about it in terms of like capital E ethics, in the sense that, like, you know, we can't derive the individual or talk about, you know, physics, as he's saying, in any kind of classical sense, or even like Spinoza's sense of like capital E ethics. But the way I read individuation and transduction and all these things, like, there seems to be a very obvious directionality to that as well, that seems to kind of like link up with what I was saying before. So whether he himself acknowledges it, or this is just something that later thinkers like Deleuze and other people will pick up on, you know, is it more that he's saying, you know, the formal philosophical systems of ethics, you can't use those to derive these things, but that they're, or maybe just us as students, like, can we read could there be, you know, an ethical lowercase e reading of these things, in the sense of kind of that like Bakhtinian sense I was saying, like the emotional, volitional directionality or orientation that is kind of inherent in any kind of process of individuation, or even participating in it, like thinking about it. I don't know if that makes sense.
So I think if I understand correctly, you're talking about or making a distinction between ethics in the sense of an ethical theory or ethical system, and then ethics as something like a general orientation of action or something like that. Yeah, so he's primarily talking here about systems of ethics, the Epicurean and the Stoic systems. I think he would still want to say that that we can't have a physical notion of the individual which is not determined by ethics in the second sense, either by some sort of orientation towards being or something like that, or orientation of behavior, or whatever you want to, however you want to call it. But I think more at a higher level, the process of thinking, or the process of doing philosophy is itself an act of individuation. It's a way in which a human being individuates themselves and brings about an individuation in thought, and there's a sort of ethical component to that, in the sense that it is an orientation of I think maybe I'm just sort of rethinking what I'm saying here, but I think maybe it would be a better way to capture it would be to describe it as an existential rather than an ethical orientation, so that thinking is always oriented. Thinking is something that a living individual does. For Simondon, it's always related to a living being, and it's a process of individuation of that being. So in that sense, there's this orientation to it, but I think he wants to preserve some notion of the objectivity of the physical notion of an individual, so that it wouldn't be relative to something like an orientation. It's we have the capacity through physical science to have knowledge of the reality of individuation, of real individuals outside of us. So that's something that he wants to hold on to.
Yeah, what's interesting is when he's criticizing the atomists here, he seems to be criticizing them for not having finality. So he says, this is, I guess, some ways in, near the end of the paragraph actually, emerging from a Kleinemann without finality, relation remains pure accident, and only the infinite number of encounters in the infinity of elapsed time has been able to lead to many viable forms. And and before, relation depends on being, and nothing substantially grounds it in being. And so it seems like Simondon is after some notion of finality here, which is actually oddly Aristotelian. But, so with all the caveats that we've read about hylomorphism and so on, but it seems like he wants relation to be grounded in something like a final cause, whereas that's what was missing in these atomists. And they just replaced it with pure chance, it seems.
I think actually the way I would articulate it is the other way around. So it's not that relation is grounded in finality, but finality is grounded in relation. What Simondon is criticizing the atomists for is not so much the lack of finality, it's the lack of relationality. It's the fact that for them, the atom is a simple entity. It's a simple principle of being, which has there's nothing that accounts for how it relates to any other being, but and then the chance sort of plays a role of filling in that gap. It accounts for relationality without having without grounding it in the being of the atom. It's just something external to the atom itself. So there's no grounding of relationality in being. Relation, insofar as it occurs, is something external to being. I don't think finality is really the category that he's looking for here. I think what he's saying is that the absence of finality in the atomistic system.
I always call back to that quote from page 15 of the text where he says, he's talking about why I believe transduction is not dialectical. And he says, it's not about there being a second stage negative, but an immanence of the negative within the initial condition through the ambivalent form of tension and incompatibility. So it's not a substantial negative, and et cetera, et cetera. But then he says the statement, even time itself is an expression of the dimensionality of the being that is individuating. So I think it gets difficult to talk about even an idea of finality because, like, I think this citation is like indicating it's even the notion of a kind of linear time like that is a product of the individuating process. Because if we remember in the pre-individual state, at least as I understand it, before there's any phase shifting for Simondon, it's as though I don't want to say it's timeless. I don't know if that's explicitly possible for him, but that individuation hasn't occurred yet, and once the phase shifting begins, you get this kind of circularity. There's not a very clear order from one phase to another, and phases can become each other, as we've seen with some of the charts. So it kind of obfuscates this thing of finality, I think.
Yeah, that's an interesting connection. I hadn't thought of it in those terms, but I think you're right that one of the criticisms that Simondon makes of the dialectic process, or how he distinguishes his own transductive process from the dialectical process, is the linearity of the dialectic as he understands it. The idea that there's a sort of fixed sequence of stages through which the dialectical process goes, whereas the transductive process is not fixed in that sense. It's a dimension that you can go back and forth along. I think a notion of finality seems to require something like linearity, something like an endpoint towards which a process is directed. Whereas for Simondon, it's not so much an endpoint that we want to think about. It's the dimension along which that action occurs. And it can occur in different directions. So, yeah, I don't think what Simondon thinks is missing from the atomistic physics is finality as such. I think it's the absence of finality is sort of a symptom of the absence of a conception of relationality, which is the real lack. So yeah, it's that relationality. It's the fact that there's no account for how being comes to be related or how an atom comes to be connected to another atom other than just chance, which is almost a negative conception. So before we move on, I think we can probably move on, but there's just one point of translation that I wanted to mention is because it sounds weird in English, but it's perfectly normal in French. If I can find it. So in English, it says, it has been said that the atom is minted Iliadic being. This is, so in French, we have simonie, which you could translate, sorry, we have ommonie. So you could translate that as minted. That would be sort of like the literal translation. But here, what it means is something like broke up. The atom is broke up Iliadic being or divided up Iliadic being, I think would be a better translation. So if you're wondering what the mint was doing here, then that's sort of why I think it's just a too literal translation. So we can go on to the next page or so, if someone else would like to read.
There is a symmetrical postulate in the Stoic doctrine. There, man is no longer a true individual. The only true individual is unique and universal. It is the cosmos. Only the cosmos is substantial, one perfectly bound by the internal tension of the pure technicon. I'm not going to try to pronounce that. This creative fire, also called seminal fire, pure spermaticon, is the principle of the immense pulsation that animates the world. Man, an organ of this great body, can only find a truly individual life in harmony with the rhythm of the whole. This harmony, which is conceived as the resonance that harp makers create through the equality of tension of two chords of equal weight and length, is a participation of the activity of the part in the activity of the whole. Although rejected by the atomists, finality plays an essential role in the system of the Stoics. This is because relation is essential for the Stoics, since it elevates the part that is man all the way up to the whole that is the cosmos individual. Conversely, for the atomists, relation can only distance man from the individual, i.e. the element, by engaging him in a participation that is in fact disproportionate with the individual's dimensions. In this sense, the ethical intention needed to turn to physics in two opposite directions. For the atomists, the veritable individual is infinitely below man's order of magnitude. For the Stoics, it is infinitely above. The individual is not sought on the order of magnitude of the human being, but at the extremities of the scale of conceivable magnitudes. In both cases, the physical individual is sought with a rigor and a force that indicate how much man feels his life engaged in this search. And it is perhaps this very intention that led the Epicureans and the Stoics to not want to take up a common and everyday being as the model for the individual. The atom and the cosmos are absolute in their consistency because they are the extreme limits of what man can conceive. The atom is absolute as non-relative to the degree attained by the process of division. The cosmos is absolute as non-relative to the process of addition in the search for definition through inclusion, since it is the term that includes all others. The only difference, which is quite important due to its consequences, is that the absolute of the whole envelops relation, whereas the absolute of the indivisible excludes it.
So here we're looking at the opposite side of the relationship between physics and ethics. We have in the Stoics, we have a physics based on the cosmos as the as what includes all, what contains everything, and the so in the ethics, we'll see in a little bit the actual sort of ethical principles tend to be actually quite similar between the Epicurean and the Stoic school, but they arrive at them from sort of opposite directions, so that the Epicurean school is sort of a bottom-up approach to the foundations of ethics, in the sense that it's modeling the individual human being on the atoms that that are the simple principles of being, whereas the Stoics are basing ethics on inclusion within the cosmos, and so the notion of cosmopolitanism is a very important one for Stoic ethics. And so in each case, they proceed in opposite directions, but they end up at sort of the same results.
I mean, we saw finality here brought up, so that seems like he's going to try to address that, which is good. And I was just going to say that, as usual, this distinction, like his critique of holomorphism, it seems very similar to the Bergsonian distinction and critique of realism and idealism as both kind of ultimately relying on a static notion of substance. I'm interested in where he takes it, because I know Simondon's project differs from Bergson's, but he owes, I guess there's like an inheritance there as well. But yeah, I just wanted to note that. I don't have much more to say about that. So Angus has this footnote here is this footnote 4 from Plutarch? Roughly refers to the constructive fire that breaches the whole. Okay. Did you have the previous footnotes as well? Or were they not significant? All I said was just that the critique of hylomorphism in Simondon and the critique of, and when he's talking about the ancients here, it seems like another kind of Bergsonian move. And even though the projects are different, I know I've been reading supplemental material all week on Simondon and Bergson. So there's just an inheritance there that I think is interesting. And when I have a more interesting thought to share, maybe I'll do it. I just wanted to note that this thing of sort of this move of showing that both of these seemingly opposite stances ultimately they kind of collapse into each other and rely on a similar notion of or a notion of substance, just at kind of different scales, seems significant to me. Maybe we can pull out some other stuff from these paragraphs.
I think you're right that this is a sort of Bergsonian move, setting up these sort of two opposed positions and showing that they're sort of mirror images of each other, and then trying to have a third position that sort of overcomes that opposition or the common presupposition of those two opposed positions. Yeah, this is a sort of a move that Simondon does pretty frequently. So Angus mentioned the comments on Spinoza and Leibniz in the previous chapter, where he describes the monads as being sort of a broken up notion of substance, but still preserving the same essential presupposition that being is primarily substance. So it's the same type of move that he's making here. One point that I wanted to sort of bring up in this bit was when he talks about. So he says, in both cases, the physical individual is sought with a rigor and force to indicate how much man feels his life engaged in this search. And it is perhaps this very intention that led the Epicureans and the Stoics to not want to take up a common and everyday being as the model for the individual. So here's another way that the I guess existential dimension of thinking determines the physics, so that because the role of the individual is something so important in that existential sense, or for something like an orientation of a living being, that we sort of because it's so important, we can't just take something every day as a paradigm of what an individual is. We have to either choose the atom as the absolutely indivisible, or we have to choose the cosmos as the absolutely all-containing entity. Either case, we have to pick something that is beyond the realm of everyday discourse as our model of the individual, because we recognize in the ethical or existential sphere or aspect that individuation is something important and that goes beyond the everyday. So there's a sort of determination of the physics by the existential or ethical aspect.
Something like the virtual is so important to a thinker like Simondon and his discussion of crystals, and crystals as like the paradigmatic example, because when you're trying to get away from both finality and the complete like accidental causality of like the Kleinemann, you need to have an account for becoming and change that is purposive in the sense that it relates to actual like structural elements that exist in a system, but that does not necessarily produce consistent results, and that can kind of infinitely variegate and evolve and transform. And there's a lot there, I think, that we could talk, I guess, as we continue to read about. Like, it strikes me very similar again to like a Bergsonian notion of élan vital. There's a way of allowing for a kind of what's the quote I read recently? And this is a quote that I thought was helpful for me, and it's actually talking about Bergson and the élan vital. It said, Bergson's, and his notion of the virtual is a non-actual dimension always on the verge of actualizing itself. It precedes every actual entity, and it's for him, it's a metaphysical force that guides the evolution of reality, actualizing itself in multiple ways. I don't think that's you can't map that on one-to-one to Simondon, but I think the idea of you need to be able to account for ontogenesis for something like, in the example of the crystal, its ability to continually individuate and have those potentials latent without them necessarily individuate in a specific direction that you could know beforehand. So you can go backwards. The retrograde movement of the true, as Bergson calls it. You can go backwards and you can trace a genealogy and you can kind of see how it happened, but you can't go back and then create a bunch of possibles out of that as though there were these equal kind of directions it could have gone. It's more complex than that, I guess.
I think Simondon, as far as I can remember, he doesn't generally use the term virtual, or at least he doesn't make it into like a sort of a category of his thinking the way that Deleuze does. What he constantly refers to is potential energy, and it's the potential energy of the system that brings about the work that is the individuation process. So that we talked about the three conditions that sometimes turn out to be two conditions, but it's the energetic condition is one of the key conditions of individuation, alongside the structural and then sometimes the material condition, depending on whether that's separated out as a third one.
I'll just start. Perhaps we need to see in this search for an absolute individual outside the human a desire to seek that does not submit to the prejudices that arise with the integration of man into the social group. The walled city is repudiated in these two discoveries of the absolute physical individual, through a self-folding in Epicureanism, through surpassing and universalization in the Stoicism of cosmic citizenship. This is precisely why neither of the two doctrines manages to think relation in its general form. The relation between atoms is precarious and amounts to the instability of the composite. The relation of part to whole absorbs the part in the whole. Thus, the relation of man to man is approximately similar in the two doctrines. The Stoic sage remains autarkes kai apathes. He considers his relations with others as part of the ta'uk ef hemen. It'd be great to have those footnotes if we can. The Enchiridion of Epictetus compares familial relations to the occasional gathering of a hyacinth bulb that a mariner encounters while taking a short stroll on an island. If the boatswain shouts that it is time to leave, there is no longer a moment to be delayed by this gathering. The mariner would risk being pitilessly abandoned on the island, for the captain does not wait. Book 4 of Lucretius's On the Nature of Things similarly treats the human passions based on yearnings, and it partially reduces their meaning to a rapport of possession. In Epicureanism, the only veritable relation is that of man with himself, and in Stoicism, the only veritable relation is that of man with the cosmos. Thus, the search for the fundamental physical individual remained fruitless in the ancients because it was too often diverted for ethical motives towards the discovery of a substantial absolute. In this sense, the moral thought of Christianity no doubt has indirectly and sufficiently provided a service for the research of the individual in physics. By having given a non-physical foundation to ethics, it has unleashed the research of the individual in physics from its moral principle, thereby liberating it.
Yeah, that's the passage that I mentioned a little bit earlier, where he argues that Christianity, by providing this ethical notion of the individual that is not founded on a physics, or that's not tied up with a physics, it frees physics from the relationship with ethics, and then allows us to understand, to have a physical notion of the individual that is not just sort of copied from the ethical notion of the individual. I mean, this is actually one point that he doesn't really develop in that other piece on the history of the notion of the individual, which is kind of surprising. But it's an interesting argument that I haven't seen made anywhere else besides here. Right, and someone has posted in the chat here a quote from a Simondon glossary about the concept of real potential, and as being something that is irreducible to either the possible or the virtual. I think that sounds right to me. I'm not sure about the virtual, just because, as I said, it's not a notion that Simondon really makes use of a lot. So that, I'm just not sure that it would make sense to make that claim. I don't know if there's enough in Simondon to say that, but it definitely is not, the potential or potential energy is definitely not reducible to something like a possibility in Simondon. It's not like a copy of reality. The standard Bergson argument about how the possible is sort of copied from reality, I think it is something that Simondon adopts as well. Oh, and then just a note on that phrase that so footnote 6 translates that phrase, the Greek phrase "taouk ethemin," is that which is not in our power. And this was a sort of a standard notion in Stoicism, is that we should, our ethical life should be based on what is within our power, which is our own thoughts and volitions and so on. And then we should sort of remain untouched by anything that is outside of our power. And so this was why you could be a free person in the Stoic sense, whether you're a slave or an emperor. It's all the same. Those are all just external circumstances, and true freedom is something that has to do with what is in our power and what we can control, rather than these external circumstances. And so that's what that's what that notion means here. And so any relationship with others in the Stoic system is understood as being something external and outside of our proper sphere of ethical life in that sense, for the Stoics.
Does anyone have that Epictetus on hand, or could we? Maybe I'll look for it while we're reading the next sections, because I would actually love to read the original passage about the mariner. Or is it Lucretius? No, it's Epictetus.
Yeah, that one is from Epictetus, and then Lucretius talks about the passions and the relationship with instincts. That's the next bit there. Okay, so let's go on to the next couple paragraphs, and we'll finish this subsection. Since the end of the 18th century, a functional role has been given to a discontinuity of matter. Airy's hypothesis on the reticular constitution of crystals is an example of this. Furthermore, in chemistry, the molecule becomes the center of relations and no longer merely a depository of materiality. The 19th century did not invent the elementary particle, but it continued to enrich it with relations to the extent that it robbed the particle of substance. This path has led to the consideration of the particle as bound to a field. The final step of this research was accomplished when it was possible to measure, in terms of the variation of energetic levels, a change of the structure of the edifice constituted by particles in mutual relation. The variation of mass linked to a liberation or an absorption of energy, and thus to a change of structure, profoundly solidifies what relation is as equivalent to being. Such an exchange, which allows to state the rapport that measures the equivalent of a quantity of matter and a quantity of energy, and thus the equivalent of a change in structure, demolishes any doctrine that connects the modifications of substance back to substance as pure contingent accidents, without which substance remains unmodified. In the physical individual, substance and modes are on the same level of being. Substance consists in the stability of the modes, and the modes consist in the changes in level of energy of substance. Relation was raised to the status of being the moment the notion of discontinuous quantity was associated with the notion of the particle. A discontinuity of matter that would merely consist in a granular structure would still fail to deal with the majority of problems raised by the conception of the physical individual in antiquity. The notion of discontinuity must become essential to the representation of phenomena in order for a theory of relation to be possible. It must not only apply to masses, but also to charges, to the positions of stability particles can occupy, and to the quantities of energy absorbed or expended in a change of structure. The quantum of action is the correlative of the structure that changes through abrupt leaps without intermediary states. Yeah, this bit is a sort of a transition to the next subsection. And so some of it take the form of sort of assertions that we just have to take on faith at this point, and they're only demonstrated in the next subsection or later. So he's going to look in the next couple sections at the relationship between particles and fields in physics, so this is basically the whole of 19th century physics was about that relationship and the increasing predominance of a concept of a field and clarification of that concept. And so the field is sort of the representative of relation, whereas the particle is initially conceived as something substantial that would only secondarily be related. And then over the course of that 19th century, we end up with a much more integrated conception of the relationship between particles and fields until in the 20th century, we have a sort of complementarity of those two concepts in the sense that, as we'll see in a little bit, light, for example, behaves in some respects like a particle, and in other respects like a wave, which is related to an electromagnetic field. What he points to in that first paragraph that I just read is the way that there's a reciprocity of mass and energy in the sense that that there's an absorption of energy in the formation of a certain structure and or an emission of energy in the transformation of structure. And so there's you can measure the equivalence of energy and mass. You can show the passage from one to the other. And so that it's, as he says, it demolishes any doctrine that connects the modifications of substance back to substance as pure contingent accidents. So any doctrine that would treat the relations in which the substance is found as something secondary is no longer possible once we have this reciprocity of energy and mass. And then there's a question in the chat about the which approach Simoneau takes to quantum mechanics. Does he take the Copenhagen approach? So we'll see in a little in the third section of this chapter, which we won't get to until for another couple of weeks. He actually does not take the Copenhagen approach. So he follows Louis de Broglie's double solution theory of quantum mechanics, which I won't get into now, especially because I don't really understand it. But I'll try to, when we get to that point, I'll try to explain as much as I, pilot wave stuff, exactly. But we'll get to that in a few weeks probably. So for those who maybe are wondering what this is about, is in the Copenhagen approach, quantum mechanics is understood as having these having to do with a sort of fundamental probabilistic interpretation of reality, so that these probability functions are basically all we can say about the behavior of certain systems. And a number of physicists like Einstein and de Broglie, they were dissatisfied with the idea that we could only have a probabilistic understanding of reality. And de Broglie proposed two different but related theories, and they're both based on the idea of an underlying causal structure, which sort of produces the behavior that looks probabilistic from our perspective, but there's an underlying structure that is deterministic. But again, we'll go into this more when we get to that point. But the idea here is that Simondon takes up this causal approach towards quantum mechanics rather than the Copenhagen approach, which is the sort of predominant one within physics today. And then in the last bit, those last two paragraphs just before the end of that subsection, so he talks about the role of discontinuity, and so he argues, or he just sort of asserts it here, and we'll see a better, a more developed exposition in the next section. But if we are only talking about discontinuity at the level of the atoms, then we're not really advancing beyond where the ancient atomistic physics was. Even if our conception of the behavior of those atoms is more advanced than theirs was, we're still sort of working with the same ontological structure. So what really gets the notion of discontinuity, or that pushes it beyond where the ancient atomists were, is the idea of a discontinuity of action or of energy states. And so this is one of the key principles in quantum mechanics, is that there's a fundamental discontinuity, for example, of the states that electrons can be in an atom, so that you can't have a continuous variation of energy levels of electrons within an atom. They have to belong to a discontinuous set of states. So there's and this was again something that a lot of physicists found sort of shocking when this concept was introduced at the beginning of the 20th century, because there is a long-standing idea within physics, and Leibniz sets this out. He says nature doesn't make jumps, so everything in nature would be continuous in some sense, and would be wouldn't have anything like a jump in states. And within quantum mechanics, there is something like a jump in states from one energy level to another. Natura non fecit saltum. Nature doesn't make any jumps. Um, um, but again, we'll get into this more when we get to the third section of this chapter. Yes, the God doesn't play dice quote from Einstein was again directed towards the probabilistic nature of quantum mechanics, which he and some other physicists thought meant that quantum mechanics was only a sort of superficial picture of nature. It has to do with our knowledge of various states of a system, and rather than the system in itself. We're sort of getting ahead of ourselves on the quantum mechanics bit. But we will see some in the next section. If we pass to the next section, if someone else would like to read, we'll see some discussion of quantum effects as well.
Subsection 2, the antinomy of the continuous and the discontinuous. It could nevertheless be objected that the advent of a quantum physics would be unable to nullify the need to maintain a wave associated with each corpuscle, which is only understood in a hypothesis of the continuity of propagation and a hypothesis of the continuity of the energy exchanges implicated in the phenomenon. It seems that the photoelectric effect alone summarizes this antinomy of the necessity of discontinuous quantities and the equal necessity of a continuous distribution of energy. There is a threshold for the frequency of quote-unquote photons, as if each photon had to convey a quantity of energy at least equal to the energy of the escape of an electron from metal. But moreover, there is no threshold for intensity, as if each photon could be considered as a wave covering a surface of indeterminate dimension and could nevertheless put all its energy into a perfectly localized point. Perhaps this antinomy would appear less accentuated if the results from the previous analyses could be retained in order to apply them to this even more general case. Here, unlike the case of the crystal, we no longer have the distinction between a discontinuous structured periodic region and an amorphous continuous region supporting scalar magnitudes. But synthesized in the same being and borne by the same support, we still have a structured parameter and an amorphous parameter that is pure potential. The discontinuous is the mode of relation, which is effectuated by abrupt leaps, like the leap between a periodic milieu and an amorphous milieu, or between two milieus with periodic structure. Here, the structure is the simplest, that of a particle's unicity. A particle is a particle not insofar as it occupies a certain place spatially, but insofar as it only exchanges its energy with other supports of energy in a quantum manner. Discontinuity is a modality of relation. Here it is possible to grasp what is called the quote-unquote two complementary representations of the real. And these representations are perhaps not merely complementary, but really one. This necessity of unifying two complementary notions perhaps stems from the fact that these two aspects of individuated being have been separated by substantialism, and because we have to make an intellectual effort to unify them due to a certain imaginative habit. For a particle, what is the associated field that we must join with it in order to account for the phenomena? For the particle, it is the possibility of being in a structural and energetic relation with other particles, even if these particles behave as a continuum. When a plate of alkaline metal is illuminated by a beam of light, there is a relation between the free electrons contained in the metal and the luminous energy. Here, the free electrons behave as beings equivalent to the continuum. As beings equivalent to the continuum insofar as they are distributed at random in the plate, as long as they do not receive enough energy to be able to escape from the plate. This energy corresponds to the escape potential and varies with the chemical composition of the metal utilized. Here, electrons intervene as supports of a continuous scalar magnitude and do not correspond to a polarized field. They are like the molecules of an amorphous body in a state of thermal agitation. Supposing that they were localizable, their place would not have any importance. The same thing applies for the particles of the light source. Their position at the instant when the luminous energy has been emitted doesn't matter. Photoelectric effects can be produced by the light of a star that no longer exists. I don't know if I should stop there.
Yeah, that's fine. Again, this is a giant paragraph that has sort of a continuous stream of thoughts, so that any cutoff point is sort of arbitrary. So I posted a link in the chat about the photoelectric effect, which is what he's going to be discussing in the rest of this subsection and then the following one. And so this has to do with the way that, so if you take a piece of metal and illuminate it with a light beam, then it emits electrons under certain conditions. What he points out, or what he's pointing to here, is that those conditions are different than what we would expect under classical physics. There's a threshold of frequency. So the light beam has to be of a certain frequency in order for the, or it has to be at or above a certain frequency in order for electrons to be emitted. And then that frequency depends on which metal in particular is being bombarded by the light beams. But the amplitude of the light wave, so the intensity of the light wave doesn't have the effect that we would expect under classical conditions. So you can, as he will describe a little bit later, if you increase the area of that is being illuminated while diminishing the intensity of the light, you can counterbalance the two to each other. So as long as the product of the area and the intensity remains the same, then you still get the same rate of emission of electrons, which is counterintuitive, because if you're increasing the area, that means that, or it would seem as if when you increase the area, there should be less light on each portion of that area, or each region of that area. If we think about like macroscopic effects, if you had a stream of water, for example, instead of light, and you spray that water over twice as big an area, then each point on that area will receive half as much pressure as it would otherwise. That's sort of like the model that you can use for a classical picture. But in this case, in the photoelectric effect, it's as if the light is acting with its full the full energy of the light beam is acting on each point where an electron is emitted, rather than being sort of spread out over the whole surface. But at the same time, the electron can be emitted from any point of the surface, so that the light beam is actually present at each point. I'm not sure if that sort of explanation makes sense, but yeah, it's the photoelectric effect, in short, is something that seems paradoxical from the point of view of a classical understanding of the way that light would interact with matter or with particles. So the question I don't think it's that work that can't be accounted for. I think it's that what makes it counterintuitive from a classical perspective is that the the light beam is in one sense behaving as if it's localized in one point, because there's the threshold effect, or the threshold principle, I guess we could say, that the frequency has to be above the threshold in order for the electrons to be released at all. But yeah, so it's localized to a particular point on the surface, so that the total intensity of the light beam sort of is acting at that one point to release an electron from the surface of the metal. But it also, in another sense, is not localized, because you can spread out the area, you can increase the area on which the light is acting without sort of diluting the intensity on any one point of the surface in that sense, so that you still get emission of electrons at the same rate, even though it would seem like there should be less light hitting each point of the surface. Yeah, so I hope that helps to clarify that example of the photoelectric effect. I think, is this a form of non-locality? I'm not sure if it's non-locality in the sense that that's used in relation to quantum physics. Which, so in quantum physics, non-locality generally refers to the way that quantum systems seem to be able to, so there seems to be a determination of elements of a quantum system that is not tied to special relativity, in the sense that you can have a system where two electrons are related to each other, so that one has a certain state and the other one has the opposite state. It's only once a measurement is carried out that you can determine which state one of the electrons has. But then, as soon as you carry out that measurement, you can know that the other electron has the opposite state, no matter how far away it is. And you can, by this means, you could, in principle, have something like a faster than light communication, so that you have what happens here, where I am, can give information about an event happening, whatever many light years away, which I shouldn't be able to receive information about for many years if the information is transmitted at the speed of light. So that's what is generally referred to as non-locality in quantum physics. I'm not sure if this instance here, in the photoelectric effect, would be an instance of non-locality or not. I was trying to get or trying to find someone who has a better grasp of physics to come in and help us with this section, but I wasn't able to find anyone. Yeah, that would be useful if anyone could see if they can figure out whether the photoelectric effect is an instance of non-locality or not.
So we are at, on the contrary. On the contrary, electrons behave as structured beings insofar as they are susceptible to escape from the plate. A quantity of energy that is measurable by a certain number of quanta corresponds to this change in their relation with the other particles that constitute the metallic milieu. Similarly, the state changes of each particle that constitutes the source of light intervene in the relation by means of the photon's frequency. The individuality of the structural changes that have taken place in the source is conserved as the energy of the photon, i.e., as the capacity of luminous energy to carry out a structural change requiring a determinate quantity of energy in a precise point. It is indeed known that the threshold of the frequency of the photoelectric effect corresponds to the necessity for each electron to receive a quantity of energy at least equal to its energy of escape. We are led to posit the notion of photon to explain not only this rule of the threshold of frequency, but also the very important fact of the distribution, or rather the availability of luminous energy at each of the points of the illuminated plate. There is no threshold of intensity. However, if the electron behaves as a particle in the sense that each electron requires the supply of a determinate quantity of energy to escape from the plate, it could be thought that it will behave as a particle also in the sense that it will receive a quantity of luminous energy proportionate to the opening of the angle under which it is seen from the light source, according to Gauss's law. This is, however, what the experiment contradicts. When the quantity of light received by the plate on each unit of surface decreases, there should come a moment when the quantity of light would be too small for each electron to receive a quantity of light equivalent to its escape energy. Yet this moment never arrives. Only the number of electrons extracted per unit of time diminishes proportionate to the quantity of light. All the energy received by the alkaline metal plate acts on this particle that is 50,000 times smaller than the hydrogen atom. This is why we are led to consider that all the energy conveyed by the light wave is concentrated in one point, as if there were a corpuscle of light.
Right, so that's what I was trying to explain there. The reason why the light wave is depicted as a photon or as a particle of light in this instance is because it has a sort of all or nothing effect. No matter how much you diminish the intensity of the beam of light. So there's a certain minimum quantity of energy that has to be transmitted to the metal plate in order for an electron to be emitted. And so it would seem that if you diminish the intensity of the light beam, eventually you should get below that intensity, that threshold of energy, so that you would have a cutoff where there would be no more emission of electrons. But what turns out to happen is that you just, if you decrease the intensity of the light beam, you just get a lower rate of emission of electrons. There's no sort of minimum intensity of light. You don't get a cutoff effect. You just get a gradual decrease in the number of electrons emitted per unit of time. And so the way that this is interpreted is that it's as if all the energy of the light beam is concentrated at one point of the surface. So that he points out this electron, which is 50,000 times smaller than a hydrogen atom, which itself is already something tiny in macroscopic terms. This one point on the surface seems to receive the whole energy of the light beam, so that it still emits. So the surface still emits electrons, and that's what's counterintuitive about this photoelectric effect. Okay, no one seems to have much to say about this bit. It takes a little while to sort of get your head around some of the concepts here. But yeah, Wikipedia has some useful articles on quantum physics to look into, just to sort of familiarize yourself with some of these notions. But yeah, I'll try to explain as much as I understand as we go along. But let's continue to the next subsection, if someone else would like to read. Oh, yeah, sorry, there's a question before we go on from Angus. So what does continuity and discontinuity mean here? So in the case of, so in quantum physics, in connection with the electron, so the discontinuity here is so it's not just, so as he points out, we can potentially localize an electron in space. We can point to where it's located, although that is a little bit difficult to do in quantum physics. But that's not the sort of primary sense of discontinuity that he has in mind here. It's the discontinuity of energy states. So the way that the electron it has this all or nothing effect in relation to the light that hits the metal surface, so that the electron either absorbs enough energy so that it will be emitted from the surface, or it doesn't. It has a discontinuous a set of energy states, or a discontinuous set of behaviors. So there's no middle ground. And then as he points to, in the whole plate, or the plate considered as one surface, the mass of electrons is behaves as a continuum, in the same way that, as we saw in the last chapter, the whole mass of the amorphous substance, all the particles within that substance behave as a continuum. So here it's just through the action of large numbers, that the set of electrons in the metal plate acts as a continuum, but it's, or I guess, a simulacrum of a continuum. And yeah, so there's the continuity in that sense, or the appearance of continuity, and then there's discreteness or discontinuity in the energy states. Okay, so would someone else like to read the beginning of the next subsection?
I can read. I'll just read to like most of the way down the next page, I guess. There's another long scientific description. Subsection 3, the analogical method. However, should the value of reality be granted to the notion of the photon, it is no doubt fully valid in the physics of the as-if, but we should ask whether it constitutes a real physical individual. This is required by the manner in which the relation between electrons and luminous energy is effectuated, i.e., ultimately between the state changes of the particles of the light source and the state changes of the particles of the alkaline metal. In fact, perhaps it is risky to consider luminous energy without considering the source from which it originates. Conversely, if we merely want to describe the relation between the light source and the free electrons of the alkaline metal, we will see that it is not absolutely necessary to involve individuals of light, and that it is even less necessary to resort to a quote-unquote probability wave to account for the distribution of the luminous energy conveyed by these photons onto the surface of the metal plate. It even seems that the hypothesis of the photon is difficult to conserve in cases where an extremely small quantity of light arrives on a large enough surface of the alkaline metal. The escape of electrons is then sensibly discontinuous, which can be translated into a quote-unquote background noise or shot noise, characterized when the currents produced in a circuit by electrons escaping from the metal are amplified and transformed into sound waves as they are collected on an anode due to the difference of potential created between this anode and the plate of photo-emitting metal, which becomes a cathode. If the intensity of the luminous flux is reduced further while the surface of the alkaline metal plate is increased, the number of electrons escaping per unit of time remains constant when the two variations are compensated, i.e., when the product of the surface illuminated by the intensity of the light remains constant. However, the probability of an encounter between a photon and a free electron diminishes when the surface of the plate increases and the intensity of the light decreases. Okay. Indeed, by acknowledging that the number of free electrons per unit of surface remains constant for every surface, we find that the number of photons diminishes when the surface increases, and when the total quantity of light received per unit of time on the whole surface remains constant. We are therefore led to consider the photon as being able to be present everywhere at each instant of the surface of the alkaline metal plate, since the effect only depends on the number of photons received per unit of time, and not on the concentration or diffusion of light on a larger or smaller surface. The photon encounters an electron as if it had a surface of several square centimeters, but exchanges energy with the electron as if it were a corpuscle on the electron's order of magnitude, i.e., 50,000 times smaller than the hydrogen atom. And the photon can do all of this while remaining capable of appearing in another effect happening at the same time and under the same conditions as linked to a transmission of energy in a wave form. Some bands of interference on the cathode of the photoelectric cell can be obtained without disrupting the photoelectric phenomenon. It would then perhaps be preferable to account for the contradictory aspects of the photoelectric method through another method, or photoelectric effect through another method.
Right. So here he's presented the motivation for the notion of a photon. Why we introduce this notion, or why it seems useful to describe light as having this corpuscular structure in certain instances in relation to the photoelectric effect. And then now he's going on to ask whether we should accord a status of reality to this representation of light. So should we understand light as having a corpuscular structure? And so he sort of gives away his answer at the beginning there. He says that we shouldn't grant the photon a status of a real individual. But his reasons for that are going to be developed over the course of this section and the following one. So the effect that he is pointing to in that passage is what I was describing about the relationship between the surface area illuminated and the intensity of the light. So that it would seem, from a classical point of view, it would seem that increasing the surface area with constant intensity of light would mean that each photon or each particle of light has a lesser chance of meeting an electron. It's as if you're sort of dividing up the amount of energy by a greater surface area. But what we find in effect is that it behaves in the opposite way, so that if you diminish the intensity of the light beam while increasing the area illuminated, you can actually compensate for the diminution of the intensity of the light beam, so that as long as the product of that intensity and the area stays the same, you get the same rate of emission of electrons from the metal surface. And so this is what is strange or unexpected about the photoelectric effect. On the one hand, the photon is behaving as if it can act over a surface of several centimeters on the metal surface. It can find an electron, or it can strike an electron anywhere on that surface. But then, on the other hand, it's acting as if all of the energy it carries is localized at that one point where the electron is, which is, as he said, is 50,000 times smaller than a hydrogen atom. So we seem to have these two different ways of the photon seems to have these contradictory properties that are hard to reconcile with each other. And then he also points out that while this photoelectric effect is happening, so while you're illuminating a piece of metal with a light beam, and that effect has to be understood in terms of in corpuscular terms, in terms of photons. At the same time, you can also produce effects in the light beam that have to be understood in wave terms, or that are in quantum physics or in our physics as it is generally understood, are presented in light in terms of waves. So he talks about the sorry, let me just find that. Right, so he talks about the bands of interference. So if you, for example, so independently of the photoelectric effect, if you just shine a light beam through a two-slit apparatus, so like an obstacle with two slits in it, then the light beams that pass through each of those slits will interfere with each other, and you get a series of dark bands on the wall behind the two slits. And you can produce this, and so this effect is understood in wave terms. It has to do with the way that the two waves of light are interfering with each other. But you can produce this wave effect, the interference, which is understood in wave terms. You can produce this at the same time as that same light beam is being used to produce a photoelectric effect, which has to be understood in photon or particular terms. So the same light beam can produce one effect, which has to be understood as a wave form, and then the other effect, which has to be understood in particle form at the same time. So we're left with sort of a mess where we have these concepts that seem to work in one domain, but then when we try to move to another domain, we have to use a different set of concepts. But then those two concepts seem to be, it seems like we have to apply these two incompatible concepts to the same entity at the same time. So this is the sort of puzzle that Simondon wants to try to unravel in this section and the following section. So let's go on to the next little bit. We might not have time to read the full page. I have to leave right at 4 today. But maybe if someone else could read, actually I'll read the next half page or so, and we can discuss. Okay. Indeed, if the phenomenon is considered from the aspect of temporal discontinuity that it presents when the quantity of energy received per unit of surface is extremely low, we will observe that the escape of electrons occurs when the illumination of the photoemitting plate had lasted a certain length of time. Everything happens here as if a certain amount of luminous energy was summated in the plate. Consequently, it can be supposed that luminous energy transforms in the plate into a potential energy that makes possible the modification of the state of relation of an electron with the particles that constitute the metal. This would make it possible to understand that the place of free electrons does not intervene in the determination of the phenomenon, no more so than the density of photons per unit of surface of the metallic plate. We will then be referred back to the case of the relation between a structure and an amorphous substance, which manifests as a continuum even if it is not continuous in its composition. Here the electrons manifest as a continuous substance because they submit to a distribution that conforms to the law of large numbers in the metal plate. This ensemble, constituted by the electrons and the metallic plate, in which they are randomly distributed, can be structured by the addition of a sufficient quantity of energy that will allow the electrons to escape from the plate. The disorganized ensemble will have to be organized. Nevertheless, this hastily presented thesis should be critiqued. There are, in fact, other ways of increasing the metallic plate's potential energy, for example, by heating it. Then, starting at temperatures below 700 degrees Celsius, between 700 degrees Celsius and 1,250 degrees Celsius, we witness a phenomenon called the Thermoionic Effect taking place, and it is more appropriate to call it the Thermoelectric Effect. Electrons spontaneously escape from a piece of heated metal. When this metal is covered with crystallized oxides, the phenomenon takes place at a lower temperature. Here, the change in distribution occurs without the intervention of any condition besides the elevation of temperature, or at least in appearance. However, the energetic condition, namely the temperature of the metal that constitutes a hot cathode, is not fully sufficient by itself. The structure of the metal surface is also involved. In this sense, we presume that a cathode can be activated by the addition of metal traces, for example, those of strontium or barium. Thus, even in the thermoelectric effect, there are structural conditions for the emission of electrons. However, as in the case of an amorphous substance that passes to the crystalline state through the spontaneous, and even today unexplained, appearance of crystalline germs in its mass, the structural conditions of the thermoelectric effect are always present in ordinary conditions when these conditions are energetic. They are present at least on a large scale for a hot cathode with enough emitting surface, but they are present in much more discontinuous manner on a small scale. Okay, I said I wasn't going to read the whole page, but then I did. So we have just a couple minutes to discuss this. So I would suggest that we should come back to that same page next time to discuss some of the what's going on there. But what he's pointing to here is so there's the photoelectric effects that we've been talking about. So the way that a piece of metal, which is illuminated by a light beam, will emit electrons. And there's also this thermoelectric effect, which is that a piece of metal, when it's heated to the right temperature, will also emit electrons. So what the purpose of introducing this second effect is that the initial, so the photoelectric effect, as we've been discussing, it has this sort of strange interplay between the continuous and the discontinuous, it's understood essentially in discontinuous terms, in the sense that the photon, or we have to understand the light beam as acting through in this particulate manner, as if it were composed of photons, individual particles. Whereas in the case of the thermoelectric effect, we seem to have a continuous effect instead, so that it's just the relationship between the heat. The heat is introducing more potential energy into the piece of metal, which then results in the emission of electrons. So we have something that seems continuous. But again, he's going to, as we go on further, he's going to anyway, this opposition is not going to be maintained in the same sort of absoluteness in which it seems to be set out at first. Okay, so it doesn't seem like anyone has any comments on that passage. So as I said, let's go back to that same passage on page 102 when we start next time, so we can sort of get into this thermoelectric effect a little bit more. But yeah, so thank you everyone for joining in, for your comments, and sorry about the interruption, and see you all next week.